Let's work through a kinematics problem. We have a Nissan GTR, which is a fast car, can accelerate to 100 kilometers per hour in 2.7 seconds. How far has it traveled in that time? We look at what we know. We can define the initial position to be 0 because we can make the coordinate system however we like. We don't know the final position. That's what we're trying to find. We know the final velocity is 100 kilometers per hour. Since it begins from rest, we know the initial velocity is 0, and we know the time, 2.7 seconds. So we can use, or almost use, this equation. X, the final position, is equal to x naught, the initial position, plus the initial velocity, v naught, times the time that it's traveling, plus 1/2 times the acceleration times time squared. Now we know everything here except x, obviously the final position. That's what we're trying to find. We know the initial position is 0 meters. We know the initial velocity is 0 meters per second, so these two terms just go away. But we don't know the acceleration. We can, however, find the acceleration from the definition of acceleration, which is that acceleration is equal to delta v, the change in velocity, divided by delta t, the change in time. The change in velocity is the final velocity, vf, minus the initial velocity, v naught. The change in time is the final time minus the initial time, but that's just equal to 2.7 seconds. So we can use, when we work it out, we can use 2.7 seconds there. So we can calculate our acceleration. Now what we need to do is to convert 100 kilometers per hour to meters per second. In order to do that, we've got a time conversion and a distance conversion. 100 kilometers per hour. We want the kilometers to go away and end up with meters. We know that there's 1,000 meters. 1,000 meters in 1 kilometer. Now the time conversion, we know that we want the hours to go away. 1 hour is 60 minutes. And 1 minute, we want the minutes to go away. Is 60 seconds. Or if you know how many seconds there are in an hour, you can directly do that conversion rather than these two conversions here. Okay, so we see that the kilometers goes away, hours goes away, minutes goes away. It leaves us with what we want, which is meters per second. If we do the multiplications, we end up with about 27.8 meters per second as v, our final velocity. So now plugging that into our equation, here we have acceleration equals delta v divided by delta t equals v final minus v initial divided by delta t. That's equal to 27.8 meters per second, our change in velocity, divided by our change in time, which is 2.7 seconds. Do the division and we get about 10.3 meters per second squared. as our acceleration, meters per second squared, because we have meters per second divided by seconds. And meters per second squared is the units we'd expect for acceleration. So now we can go back to our equation here and calculate x. X is equal to the initial position, which is just 0 meters, plus the initial velocity times time. The initial velocity is also 0, plus the only thing that's not 0, 1/2 times our acceleration, 10.3 meters per second squared, times time squared. Time is 2.7 seconds. 2.7 seconds squared, being careful to square both the units and the number. Multiply that out, and we get, for our final answer, 37.6 meters. Our units are meters because we have seconds squared here divided by seconds squared here, and that leaves us with just meters. So our final answer is x is equal to 37.6 meters. That's the final position of the car.